Okay, so today's lecture we're going to look just at section 4.3 in the book. This is the normal distribution, and there's a fair bit of stuff in this section, so I think it'll take all of today's lecture to cover it. So probably a good way to start is by showing you what the probability density function of a normal distribution looks like. So if the random variable x has a normal distribution with mean or expected value mu and variance sigma squared, then it would have the following probability density function. So this is a function of x. It has parameters mu and sigma. And it looks like this. It's 1 over the square root of 2 pi sigma e to the minus this thing, x minus mu squared over 2 sigma squared. So that's a pretty ugly probability density function, but it has a nice shape, as we'll see in a minute. This is defined for x on the whole real line, so x can be any positive or negative number. The parameters of the distribution are the mean mu, which can be any real value, and the standard deviation sigma, which has to be positive. So in R, we would, if you want to evaluate this function in R, you can use the function dnorm. The d here stands for density. And that's why all of these R functions start with a d that give the probability density function, and in fact the probability mass function too. The d stands for density. So in R you would give it the value x that you want to use, and then specify the mean, mu, and the standard deviation, sigma. So that's how you'd calculate it. And I've used R to calculate the probability density function and graph it for a few different values of mu and sigma. So here's a graph of the probability mass function for 3 different values of mu and sigma. So the black line on the left is mu equals minus 3 and sigma equals 1. In fact, all 3 of these probability density functions have the same value of sigma. It's 1. But the only thing that changes is the value of mu shifts. So when mu shifts to minus 1 here, then the probability density function shifts to the right. It's centered over minus 1. And then when the probability density function, the third one, has mu equal to plus 1, and it shifts there. So as we've seen before with probability functions, changing the mean just shifts the distribution, basically, in these cases. So in terms of the actual form of the probability density function, you'll notice it sort of has a peak right at x equals mu, and then it tails off and comes very close to being equal to 0 as you get far enough away from mu. And if you look at the shape of these plots and think about the form of the probability density function above, you'll see that that sort of makes sense. So the probability density function looks like this, and you'll notice that when x equals mu, then this term here will be 0, and you'll have e to the minus 0, which is 1, and then you'd have a height 1 over root 2 pi sigma. So that's the maximum that this probability density function will take, because as x moves away from mu, this number will become, well, it'll become bigger than 0, and when you square it, it'll be a positive number bigger than 0. So e to the minus some positive number will be smaller than 1. And therefore this is going to decay. And as x moves farther and farther away from mu, this number will get bigger, e to the minus that number will get smaller, and you see this decay of the tail down here. So as x moves far away from mu, then the probability density function dies down to 0. And of course, for it to be a probability density function, this has to happen at some point, because the total area underneath it has to be 1. And the only way that'll happen is if it eventually decays down to 0 or cuts off entirely. It looks like the probability density function is equal to 0, but in fact it's never exactly equal to 0. It's just some very small value once you move far enough away. So that's the effect of changing mu on the probability density function. If we change sigma instead of mu, then we have a different effect. So what I've done here is I've drawn 3 probability density functions for a normal distribution with different values of mu and sigma. So the first one here is mu equals minus 3 and sigma equals 0.4. So that's a standard deviation that's less. And so in comparison to the graph above, you'll notice that the axes are the same. In comparison to the graph above, there's less variation. There's not as wide a spread to this probability density function as in the above case. The middle one has actually the same parameters. So this is mu equals -1, sigma equals 1. So in fact, the two red dotted lines are exactly the same probability density function. The only thing that changes is that the vertical scale of these two graphs is different to accommodate the one probability density function on the left that has a much higher peak. If we increase sigma further and draw the green graph on the right, this is mu equals 1. I've just chosen different mu values to sort of separate the centers out, make it easier to see what's going on. And sigma equals 3. So what's going on here is now that the probability density function is very flat and spread out. So you can see that changing sigma goes from a small sigma giving you a very sharp peak and a quick decay, a lot of probability in a small interval, to a large value of sigma giving a very gradual decay of the probability mass function and the probability spread out over a much wider area. If you look at the form of the probability mass function, probability density function above, you can see that indeed sigma does determine both the height of the peak, because it's here, so a small value of sigma makes the peak high, and it also determines how quickly the probability function decays, because this is in the denominator here. So a large value of sigma means that this whole term will get small slowly as, or the exponent will get to be a big negative number, but do it slowly as x moves away from mu, and so you get a slow decay. In any case, if that didn't make much sense, hopefully the pictures give you an idea of what's going on. I made a little note here at the bottom to talk about symmetry. The probability density function for a normal distribution is symmetric about the mean mu. So f of x is symmetric about mu. So that means mathematically f of mu minus, well, say mu minus x would be the same as the density of mu plus x. If you're some distance below the mean, it's the same as being above the mean. In pictures, what that's saying simply is that if I reflect this probability density function about the value of mu, it'll have the same shape if I flip it on that axis. So it's a mirror image in the above picture. That'll come in handy later when we talk about calculating probabilities for the normal distribution. Now there's a lot of properties of the normal distribution. Quite a lot of this section is going to cover properties and techniques and so on before we actually get to using the normal distribution as a probability model for real life phenomena. So this stuff will be a little dry, but we'll get through it reasonably quickly, I think. So some properties of the normal density. If you integrate it over the whole real line, it integrates to 1. That's important because if this wasn't true, it wouldn't be a probability density function. We require that it does integrate to 1. Now you'll notice you can prove, we're not going to in this class, but you can prove that the following integral has this solution. So if you integrate e to the minus z squared over 2 over the whole real line, you get the value 2 pi. And you'll notice that that looks a lot like, this part here looks like the unnormalized version of the probability density function. That is, it's the part without the 1 over 2 pi in front of it. And so you can sort of see that if you divide this through by 2 pi, root 2 pi, then you would get something that integrates to 1. And in fact, you can also perform various manipulations like shifting it by mu or stretching it by a factor sigma as well, and it still integrates to 1. But we'll just assume that this is true, that the probability density function does integrate to 1. Another property of the probability density function and the normal distribution is that its expected value is equal to mu. And I'll write down the formula for what this is, but I'm not going to do the derivation because it's pretty time consuming. So what we would be doing though is to evaluate the expected value of x, you'd write down x times the probability density function, which is 1 over root 2 pi sigma e to the minus 1 over 2 sigma squared x minus mu squared. I'm using a few different notations here, but it's the same function. I sometimes write exp of something rather than e to the power of all of that, just so it's clear that everything inside here is getting raised to the eth power. Or e is getting raised to that power, I guess you'd say. Other than that, this is the same probability density function. If you do that integral, you find that the expected value of x is equal to mu. And you can do a similar integral for the variance of x, which would be the expected value of x minus mu squared. So that it would be that times the probability density function, and that works out to be sigma squared. So the mean and variance of a normal distribution, parameterized the way we had it on the previous page with this form of probability density function. The mean is mu, the variance is sigma squared. And we're just going to take those at face value rather than prove them. Some notation, we'll write that x, and this squiggle is called a tilde, n mu sigma squared, that represents x has a normal distribution with mean mu and variance sigma squared, because this shorthand will be handy to write rather than having to write out x has a normal distribution with mean mu and variance sigma squared. That would be a little more time consuming. Okay. We'll see in a few minutes that it will be important to work with linear transformations of normal random variables. So if I have a random variable x that is normally distributed with mean mu, variance sigma squared, and I let y equal a times x plus b, where a and b are constants here. If I define a new random variable y, we already know from work that we did earlier this week that the expected value of y will just be a times the expected value of x, which is mu, plus b. So we're just plugging in the expected value into this formula. And the variance of y is the square of the multiplier, that's a, times the variance of x, which is sigma squared. So we already know this. We don't need to prove that. It turns out that we can also prove that y is normal as well. So if I take a normal random variable and multiply it by a constant and add another constant, it will still have a normal probability distribution. It may have some different parameters, but it will be the same distribution. So that is, we can say that starting from here, x is normal, mean mu, variance sigma squared. Y is defined as a times x plus b. That means that y will also be normal with mean a mu plus b and variance a squared sigma squared. This will come in handy for the following reason. If I have a random variable x, normal, mean, mu, variance sigma squared, if I define a new variable z, which is x minus mu over sigma, we can figure out what the distribution of that is. I could write that as x over sigma minus mu over sigma, right? So this is like the formula above with a equals 1 over sigma, and my b equals minus mu over sigma. And so we know from the above that z will have a normal distribution as well. We'll know that z will be normally distributed with expected value. Well, we would plug in mu here, mu over sigma. So we take x, we just plug in mu here. So it would be mu over sigma minus mu over sigma. And variance, well, we're multiplying by 1 over sigma here. So we would be multiplying by 1 over sigma squared times the variance of x, which is the same as saying it's normal, 0. These two cancel. 1 over sigma squared. The variance of x is sigma squared. So we get normal, 0, 1. So if we create a new random variable by subtracting away the expected value of x and then dividing by the standard deviation of x, we get what's called a standard normal. A normal random variable with expected value 0 and variance 1. So this is called a standard normal, and it's going to come in quite handy in a few minutes. So the expected value of our random variable is z is 0 and the variance is 1. Or the standard deviation is 1 too, I guess, because 1 squared is 1. The reason this is handy is that if you want to do a calculation for the probability that x is less than a, you can convert it to a calculation that involves a standard normal random variable. So for example, you can say this is the same as the probability that x minus mu over sigma is less than or equal to a minus mu over sigma. And this would be the same as the probability that z is less than or equal to a minus mu over sigma, where z is a standard normal. It's normal 0, 1. Why is that important? Well, it's important because it gives us an easy way to calculate probabilities such as this using just a standard normal distribution. So one of the problems with a standard normal distribution is that it's hard to calculate probabilities like this. There isn't a simple form. Like in the exponential case, for example, we could do the integral to calculate something like this and get a formula that was nice and easy to use. Here, if you were to integrate the probability density function to calculate this, it turns out that the integral doesn't have a nice closed form, and you have to solve it with a computer, basically. Or used probability tables. The advantage of what we're doing here is that if you were using probability tables, you'd only need to carry around one set of tables for standard normal, because you can convert a probability statement about a non-standard normal to one about a standard normal, and then look it up in your standard normal tables. This will all make sense in a minute when I show you how to do that in some examples. So what I've written here is just a summary of what I said, namely that by standardizing, we only need to know the probability that a random variable z that's standard normal is less than or equal to some constant. We'll show an example of looking these up in just a minute. We'll do a few facts first, though. One more fact. So the cumulative distribution function for a normal random variable, in fact for a standard normal, we'll work on this one first, that would be the probability that the random variable z, a standard normal, is less than or equal to some value little z. We write that as capital phi of z. So this Greek letter here is a phi. And we'll use that symbol in this course just to represent the CDF of a standard normal distribution. What it is it's the integral from minus infinity up to z of the standard normal probability density function. And I made a mistake here, actually. This sigma shouldn't be there, because in a standard normal, we assume that mu equals 0, sigma equals 1 for a standard normal. Guess I'll have to type that again. Standard normal. Okay, so that would be the integral that you'd need to evaluate. And I put a question mark here because it has no closed form solution. I mentioned that a minute ago. No formula for this. You can't write down a formula, it turns out. There are some integrals that you just can't get in closed form. Now, that's not such a big deal these days with computers, because you can approximate this integral to an arbitrary number of decimal places quite quickly and efficiently, and there are lots of programs to do that. R has functions that will do that calculation for you. So as far as we're concerned, this is sort of a non-issue. However, in earlier days, it was sort of important because not everybody had a laptop with R on it that they could whip out at any time and calculate standard normal probabilities. And so it was actually kind of important to be able to use a standard normal table with values of this for lots of different values of little z. And then use those to calculate probabilities like the ones we have above. So there are three places that you can go to calculate probabilities like this. You can use the basic statistical probabilities and tables from this course. I'll show you how to do that in a minute. You can go inside the cover of your textbook. There's a standard normal table on the front inside cover, or R will do this for you as well. And I'll show you all three of those methods in the next few pages. So let's look at some cases. And these examples all involve just the standard normal. We'll look at some examples in a minute that involve the normal distributions that have different means and variances, but let's figure out how to do this with a standard normal first. So in this course, generally when we write Z, we'll be talking about a standard normal random variable. So let's calculate the probability that a standard normal is less than or equal to 1. So I've graphed here roughly what the probability density function of a standard normal would look like. It's centered around 0 because that's the mean, and it has a bell-shaped curve that decays off pretty quickly, and by the time you're at plus or minus 2, it's close to 0, and by the time you're out to plus or minus 3, it's very close to 0. There's very little probability on either of those tails. What we're interested in here is the probability that Z is less than or equal to 1. So in terms of this graph, you can think of it as this. I should say this is a graph of the probability density function, f of x. And we're interested in, because it's a density function, the area to the left of the line, that would be probability that Z is less than or equal to 1. Or in the notation we have above, you could write that as big phi of 1 as well. So we need to calculate that probability, or look it up in a table, or use R to do that. So what I'm going to do here is I'll show you how we can look that up in a standard normal table. So I'm just going to switch to another application where I have a copy of the standard normal table open in the BSPT. So here is the BSPT, and this is part 2 of the BSPT. And if we turn to the table that has the page that has table 3 on it, these are standard normal probabilities. And I've actually skipped to the middle of the table. I'll go back to the beginning of the page. So this is the first page of the standard normal probability table. You'll see it starts at Z equals minus 4. And so what you have is a bunch of pairs of values. You have the Z value and the probability that you're less than it. And so you can see that at minus 4, there's almost no probability to the left of it. To 4 decimal places, it's 0. By the time you've gotten to minus 3, the probability is about just bigger than 0.1%, 0.0013. By the time you've gotten down to minus 2 on the next page, you've got a probability of about almost 2.5%, 0.0228. And we're interested in the probability that Z is less than 1. So we wanted to find the probability that Z is less than 1. So we have to look for a column here that has a plus 1 in it. So we need to go to the next page. We want the probability that Z is less than or equal to 1.0. So what we do is we read down the column here. And that was a particularly easy one, it turns out, because it's at the top of the column. But right here you'll see there's a 1. That's our probability. And the corresponding probability is 0.8413, according to the table. So it says there's an 84% chance that a standard normal is less than 1. So we can switch back to our other program and look that and write that in our notes. Even though you'll probably use R mostly to calculate these things in assignments, you should be familiar with how to use a table to look it up, because in a test situation, we're not going to typically use a laptop for tests, and so you'll want to be able to use the tables. But it's pretty straightforward. The tables in the BSPT are especially easy to use because you're just reading down a column. Let's do a few more of these just to get the feeling for it. Oh, before I go on, let me just note that it's usually a good idea when you're calculating these probabilities to draw yourself a little sketch of the standard normal distribution and sketch in the area that you're trying to calculate the probability for, because that'll give you an idea of whether you have the right answer. So even though my drawing skills are not good, you can see that in this case clearly the area at 0, the area to the left of 0 should be a half, because this thing is symmetric. The area under the whole thing is 1. So the area to the left of the mean 0 should be half. And so the fact that we're looking at an area of to the left of 0.1 means we better get something that's bigger than a half. And we did. So that's useful. The next question says, okay, calculate the probability that you are greater than or equal to 2. So we're interested in this area right here. And there's actually a couple of ways you could calculate this. The first way is to say, well, I don't know what this, my tables will give me less than probabilities, not greater than. So I could say that that is 1 minus the probability that z is less than or equal to 2. And then figure out the white area in the graph. I'm not going to try to shade that with a different color because that'll get confusing. And if you look that up in the BSPT, you get 0.9772. Well, actually you get 1 minus that, I suppose. That's the, 1 minus 0.9772, which is 0.0228. So that's one way you could do it. You could say, I'm after the white area. The other way is to argue by symmetry. You could say, well, this thing is symmetric about 0. So that means the probability that I'm 2 or bigger is exactly the same that I'm minus 2 or less. This is the same as the probability that z is less than or equal to minus 2. That's the opposite tail. And so if you look that up in the BSPT, you get 0.0228. In fact, that's exactly the answer we got above, but I looked this up directly in the tables. You can check the tables yourself and verify that it's true. So either one of these solutions is fine. You just have to draw the right picture. And just to help you out to see that symmetry, I'll quickly sketch that other picture here. So I don't know, let's go with green. So there's what that would look like if you were arguing symmetry. It's just the tail area here. All right, let's look at another one of these. So hopefully you're getting the hang of how to calculate these now. So what if we were to calculate the probability that z is between -1 and +2? So what that would look like is we have an interval that starts at -1 and goes to +2. So what we're interested in is this part right here. And what we can do is we can calculate that by looking at the difference between the CDF at 2 values. So we can write that as the probability that you're less than or equal to 2, which would be starting at 2 and going all the way out to the left tail, minus the probability that you are less than or equal to -1, which you would write as the CDF evaluated at 2 minus the CDF evaluated at -1. And we did some of these above, I think. Let's look back and see. Yeah, we did the probability that, oh, no, we did greater than 2. Oh, no, we looked up the probability that you're less than or equal to 2. It was 0.9772. So this is 0.9772 minus the probability that you are less than or equal to -1. If I go to the BSPT, that's 0.1587. Which gives me 0.8185, I think. And that looks like about the right value there. It could be about 80% of the probability there. Okay, last one we'll do is quite an easy one. The probability that z is less than or equal to 0. This is just to emphasize our intuition about symmetry in this case. The probability that you're less than or equal to 0 is the left half of this normal density function, the area under the left half, and this should be equal to 1/2 by symmetry. You don't even have to look that up in the table because you know that the probability on the left side should be the same as the probability on the right, and since they have to add to 1, that had better be 1/2. Before we move on to the next section, I'll just mention that you can do these calculations in R. So in R, the probability that a standard normal is less than or equal to some value, I don't know, 2.5, would be written as P norm, P for probability, and you give the value 2.5. And if you don't give any other arguments, then it will assume that mu is 0 and sigma is 1. That is, it assumes a standard normal if you don't tell it otherwise. We'll look later at cases where we give other arguments. We want to specify a mu and a sigma. But if there's no other arguments given, then it'll assume it's standard normal. So we can type in a command like that and figure out the cumulative probability. So essentially, in the examples we have above, when we get to a point where we're saying, okay, I need to go look something up for a standard normal, a cumulative probability, then you can calculate that in R. Now, just as we looked at in the general case in Wednesday, another kind of calculation we're interested in doing with a probability density function is figuring out the percentiles. Sometimes this is called the inverse CDF, but we really use the phrase percentiles mostly to represent this concept. So in the case of a standard normal, we're going to have a little bit of special notation because we use this scenario so often. What we'll do here is we'll say that we'll let z with a little alpha subscript represent the value of z, so that's a value along the horizontal axis, such that the cumulative probability up to that point, that is the probability that z is less than or equal to the value z alpha, is the number alpha. So here alpha is a probability between 0 and 1. In terms of a picture, what we're saying is I've picked an alpha that gives me a certain area. I want you to tell me what cutoff z alpha would give me that value. That's the thing that I'm looking for. So we're saying, given an alpha, find z alpha. This is the opposite of what we were doing on the previous page, because there we were saying, I have a cutoff, tell me the probability. Now we're saying, I've got a probability in mind. What cutoff gives me that probability? And it's not much harder to do it this way. So for example, let's suppose I want to calculate the 99th percentile. I want to find a value z.99 such that there's 99% probability to the left of it. What is that cutoff value? Well, if it's 99% probability to the left, we know it's going to be some large value. I don't know precisely what it is, but it's going to be something up here because we want this area here to the left. This has got to be 0.99. It's got to be some big value. How do you find that out? Well, there's two ways. One way, we can switch to the BSPT and look things up there. So let's do that now because it's good to see how we do that in one specific case. I'm going to switch to the tables here. What we're looking for, now I've forgotten what we're looking for, so I'm going to go back and check. We're looking for the 99th percentile. So what we're after is we want a probability of 0.99 in our probability column. We want to keep reading from left to right until we get a value that's large enough that exactly 99% of the probability is to the left of it. So here we are at 0, we've got 50%. At 1, we've got 84%, getting closer. At 1.5, we've got 93%. Keep reading down, 94, 94 and a half. It's somewhere between 1.64 and 1.65. So it's about 1.645. Probability that z is less than or equal to 1.645 equals 0.95. So we can go back and figure that out now. Except I don't think I was looking for 95, was I? Nope. Okay, let's keep looking then. That would be how you'd find 95. We're after 99, so we've got to go to the next page of this table and keep reading down until we see 0.990 roughly, which is about 2.33. So the probability that z is less than or equal to 2.33 equals 0.99. So we can go back and put that in our notes. 2.33. And that I actually didn't do too bad a job at guessing that it was somewhere between 2 and 3 based on my picture. You wouldn't necessarily get it that close every time, but you should hopefully know that you're expecting a positive number anyway, because we know that 50% of the probability is at 0. And after you've done a few of these, you'll start to see patterns and be able to decide when things are close pretty easily. Let's do a few more of them. If I'm looking for the first percentile, so now I'm looking for a value that has 1% below it. So I want a cutoff that has 1% below it. So again, we could switch to the BSPT and look for a value of 1%. Let's do that since I did the last time pretty badly. So we're looking for 1% in our percentages column. So at -2, we have 2.2%. We're looking for 1%. So 2.5, that's too small. Oh look, it's 2.33. Minus 2.33. I guess we should have seen that coming. Minus 2.33. So in fact, you could argue that by symmetry, because we had 99% below plus 2.33, or 1% above, and here you'd have 1% below. To do another one, well, this one is really kind of easy. But if you wanted to find a cumulative probability, a cutoff that gives you a percent, the 50th percentile, one that has half the probability, well, we know that one right off. It's 0, because the probability that z is less than or equal to 0 equals 0.5, which is what we're after. We don't need to look up in the BSPT that one. Let's do one more. So let's suppose we're looking for the 30th percentile. We want 30% probability to the left. So we know it's going to be a negative number because 50% probability is here. So let's say it's there. I'm just making up numbers. Maybe it's closer to 0 than that. But we want 30% probability there. And if I'll leave you to check this on the BSPT, but if you go there and do that, you get about minus 0.53. Now, in fact, when you're doing some of these, you'll notice that you're not getting exactly the right value. It's either minus 0.53 or minus 0.52. It's somewhere in there. You could try and interpolate between those values and get something that's closer, but that's a waste of time. If you want to be that accurate, use R. For testing purposes, whichever one of those is closer is fine, and in fact, either one would be fine. So don't worry about it.